An on-off key modulation, or OOK modulation, has a carrier wave and a message signal. The carrier wave is a high-frequency sinusoid. The message signal is binary. It can either be high or low. The OOK modulated signal shows the carrier when the message signal is high and nothing when the message signal is low. Let's take a look at these signals in the frequency domain. The carrier sinusoid in the time domain only has one frequency. So on the frequency spectrum, we're going to have spikes at the carrier frequency and at the negative carrier frequency. If the message signal is a rectangular waveform, we're going to have the HD sync ND. In this case, we have a square wave, so every second harmonic will be missing. Going back to the time domain, the OOK modulated signal is the result of the carrier signal multiplied by the message signal. Multiplication in the time domain is equivalent to convolution in the frequency domain, and vice versa. If we take the convolution of the carrier and the message frequency spectrums, we're going to have the HD sync ND from the square wave centered at the carrier frequency and the negative carrier frequency. To simulate the OOK modulation, we're going to go to the library browser. We're going to use a sine wave for the carrier, and we're going to use a pulse generator for the binary message signal. We want the carrier wave to have a higher frequency than the message wave, so I'm going to set the carrier wave to have a frequency of 50 Hz and the square wave to 5 Hz. For the sine wave, we're going to do sample based. We want 1000 samples per period. A 50 Hz frequency is a 0.02 seconds period, with 1000 samples making up one period and one period lasting 0.02 seconds. That would give us 1000 samples per 0.02 seconds. So one sample would last 0.00002 seconds, or 0.02 milliseconds. For the message signal being a square wave of 5 Hz, with a frequency of 5 Hz, the period is 0.2 seconds. So again, with 1000 samples making up one period, and one period being 0.2 seconds this time, there is 1000 samples per 0.2 seconds, so that means one sample would last 0.0002 seconds, or 2 milliseconds. So again, we're going to go to sample base. We want 1000 samples making up one period, and if we want a square wave, we want the pulse width to be half of the period, 500, and the sample time is 2 milliseconds, or 0.0002 seconds. To get the OOK modulated signal, we're multiplying the carrier wave by the message signal. So we're going to get a product block. We're also going to get a scope and a spectrum analyzer. I'm going to go here and I'm going to change the layout. For the spectrum analyzer, I'm first going to connect it to the sine wave, and I'm going to run it. So here I'm going to go to settings, and I'm going to make some adjustments so I can view it better. If we turn on the peak finder, you'll see that we have the 50 Hz carrier wave on both sides of the spectrum. And then I'm going to make a copy of this and paste it 2 times. Now we can connect the spectrum analyzer to the square wave and the modulated wave. Alright, let's run it again. Alright, first let's check the scope. So we have the carrier sine wave here, the binary message signal here, and the OOK modulated signal here. So whenever the square wave is a 1, you'll see the carrier wave present, and when it is 0, you'll just see a flat line at 0. And then the frequency spectrum of the square wave. The frequency spectrum of the square wave is in the shape of the sync function, in which the duty cycle is 0.5, so every second harmonic is missing, and the fundamental is 5 Hz. For the spectrum of the modulated signal, you would see that we have the shape of the sync function from the square wave centered at 50 Hz and negative 50 Hz, because that is the frequency of the carrier wave.